What if I told you the entire universe might be moving in a direction it shouldn't be? Picture this: countless galaxies, trillions of stars, all drifting together like leaves caught in some unseen cosmic river, defying everything we thought we knew about space. This isn't science fiction. It's a real, spine-tingling mystery astronomers call dark flow, and what we've discovered so far will rewrite how you see the fabric of reality itself. For centuries, we believed the universe expanded evenly in all directions, a grand but predictable dance of matter and energy. Then, in 2008, scientists made a discovery that sent shockwaves through astrophysics. They found clusters of galaxies hurtling towards something beyond the edge of the observable universe, something so massive, so unimaginably powerful, it's tugging at everything we can see. This isn't just a few stray galaxies. It's a colossal current sweeping through the cosmos, and no one knows what's causing it. That's where the real magic begins. Over the next few minutes, we're diving into 30 jaw-dropping facts about dark flow that will bend your understanding of space, time, and perhaps even the nature of existence. From the eerie speed of this motion, faster than anything our physics can explain, to the chilling possibility that our universe is being pulled toward another, unseen reality, every twist will leave you questioning what lies beyond the stars. Buckle up, we're about to explore one of the universe's greatest enigmas, and by the end, you'll never look at the night sky the same way again. The first clue emerged from the faintest whispers of the cosmos, the afterglow of the Big Bang itself. In 2008, a team of astronomers poring over data from the Wilkinson Microwave Anisotropy Probe, or WMAP, noticed something that shouldn't exist. This spacecraft had mapped the cosmic microwave background, the oldest light in the universe, with unprecedented precision. But buried in that data was an anomaly. Hundreds of galaxy clusters, each containing thousands of galaxies, weren't just drifting apart as the universe expanded. They were racing toward a single, mysterious point beyond the edge of everything we can observe. At first, scientists thought it might be a flaw in the measurements. But when they cross-checked with X-ray data and galaxy surveys, the signal only grew stronger. These clusters were moving at speeds exceeding 1,000 kilometers per second, far faster than the known forces of gravity could explain. Even more baffling, the direction. From our vantage point, it's as if the universe has a hidden north, a gravitational epicenter so powerful it's bending the motion of galaxies like a magnet tugging at iron filings. What makes this discovery so revolutionary is how it defies cosmology's bedrock principle. The universe should look roughly the same in all directions. Yet here was evidence of a colossal flow, a current so vast it spans billions of light years. Some researchers argue it's the gravitational pull of a structure beyond our cosmic horizon, perhaps a supercluster of unimaginable scale, or even another universe brushing against our own. Others suggest it might force us to rewrite Einstein's laws of gravity itself. One thing's certain, dark flow isn't just a curiosity, it's a crack in the foundation of how we understand reality. Now, let's talk about just how fast this cosmic current is ripping through the fabric of space. We're not talking about a gentle drift. These galaxy clusters are hurtling at mind-blowing speeds of up to 1,000 kilometers per second. That's over 3.6 million kilometers per hour. To put that in perspective, if our solar system were caught in this flow, we'd cross the entire distance from Earth to the Sun in less than 2 days. What makes this speed so unsettling is that it defies every established rule of cosmic motion. According to our current understanding of gravity, the pull of visible matter, stars, galaxies, even dark matter shouldn't be strong enough to explain this kind of velocity. It's like throwing a ball and watching it accelerate long after your hand has left it, as if some invisible force keeps yanking it forward. Even stranger. The flow isn't slowing down. As these clusters race toward the unknown, their speed remains eerily consistent across vast distances, suggesting whatever's pulling them isn't just massive, it's actively exerting influence. Some theorists speculate this could mean the gravitational footprint of another universe, one so close its gravity leaks into ours like a shadow pressing against a curtain. Others argue it might hint at flaws in Einstein's theory of general relativity, a crack in the equations we've trusted for a century. Yet the most haunting possibility is this: dark flow might be evidence that our universe isn't the only one. That beyond the black void of our cosmic horizon, something unimaginably vast is out there, warping the very fabric of space-time, and it's pulling us toward it. Here's where things get even stranger. Dark flow isn't just a random cosmic drift. Every single galaxy caught in this mysterious current is being pulled toward the exact same patch of sky, a region near the constellations Centaurus and Hydra. Picture standing on a beach, watching thousands of leaves floating on the waves, only to realize every single one is being dragged toward the same invisible whirlpool. That's the level of eerie precision we're dealing with. This directionality shatters one of cosmology's most fundamental assumptions, that the universe expands uniformly in all directions, like a balloon inflating evenly. The Big Bang's afterglow, the cosmic microwave background, should look nearly identical no matter where you point your telescope. Yet dark flow's pull creates a bizarre cosmic tilt, as if the universe itself is leaning toward something colossal just beyond our sight. What makes this target so perplexing is its scale. The pull isn't coming from anything we've mapped, not a supercluster, not a void, not even the mysterious Great Attractor, a known gravitational anomaly in our cosmic neighborhood. This is something far larger, something so distant it lies beyond the observable universe's edge. Some calculations suggest it would need to be hundreds of times more massive than the entire visible cosmos to exert this kind of influence. And here's the kicker: the direction aligns almost perfectly with the so-called axis of evil, a controversial pattern in the cosmic microwave background that some scientists argue hints at a fundamental asymmetry in the universe. Could dark flow be the smoking gun proving space itself has a hidden architecture, a preferred direction woven into the fabric of reality? Or is it evidence of something even more extraordinary, like a neighboring universe brushing against ours, its gravity leaking through the cracks between dimensions? One thing's certain: every time we point our telescopes toward Centaurus and Hydra, we're not just staring at stars, we're peering into the universe's greatest blind spot, a place where the rules of physics as we know them might not apply. And whatever's out there, it's pulling us closer with every passing second. Here's the cosmic paradox that keeps astronomers awake at night: dark flow isn't just breaking the rules, it's rewriting them. While the Hubble expansion shows galaxies drifting apart like dots on an inflating balloon, dark flow acts like a hidden hand yanking entire clusters off course. Imagine watching a river where every drop should flow outward evenly, yet suddenly you spot a powerful undercurrent dragging everything sideways. That's the universe we're dealing with. For nearly a century, Hubble's law has been cosmology's golden rule. The farther a galaxy is, the faster it moves away from us, proof of space itself stretching in all directions. But dark flow tosses a wrench into this tidy picture. Instead of galaxies scattering uniformly, hundreds of them are caught in this mysterious stream, all moving toward the same distant point while the universe expands around them. It's as if the balloon isn't just inflating, someone's tugging it sideways with unimaginable force. What makes this clash so groundbreaking is the scale. Hubble's expansion is gentle, predictable, driven by dark energy's push. Dark flow, though, it's a localized tsunami in that calm cosmic ocean. The clusters involved aren't just drifting, they're racing, as if something beyond our observable horizon is warping space itself into a colossal slope. Some scientists compare it to finding a mountain range where there should only be flat plain. a gravitational anomaly so vast it defies the universe's supposed symmetry. The implications are staggering. If dark flow is real and mounting evidence says it is, then the cosmos isn't just expanding, it's being shaped by forces we can't yet see. Maybe it's a neighboring universe's gravity bleeding into ours, or perhaps Einstein's equations need a tweak we haven't imagined. Either way, one truth is clear: the universe has secrets darker and far stranger than we ever dreamed. We've mapped the universe's hidden players: dark matter, dark energy, but dark flow might be revealing a plot twist even they can't explain. Dark matter's gravity binds galaxies together like cosmic glue, while dark energy drives the universe's accelerating expansion. Yet neither fully accounts for the sheer force behind dark flow. Imagine a tug of war where known physics says the rope should slacken, but instead it's being yanked sideways with impossible strength. Dark matter could partly explain the pull. Its gravitational web stretches across the cosmos, and some theorize an uneven distribution might nudge galaxy clusters in one direction. But here's the catch: dark flow's speed and scale dwarf anything dark matter alone should cause. Even the most massive superclusters we've found, like the Shapley Attractor, a dense knot of galaxies, don't pack enough punch to account for this motion. It's like blaming a breeze for toppling a skyscraper. Then there's dark energy, the enigmatic force stretching space itself. While it pushes the universe apart, dark flow defies its uniform influence by dragging matter toward a single point. Some models suggest dark energy might fluctuate, creating ripples that steer galaxies. But critics argue this is like using a fog machine to explain a hurricane, possible but straining credibility. The real shock: dark flow might be evidence of something beyond these cosmic staples. Quantum fluctuations from the Big Bang could have left imprints so vast they warp spacetime on scales we're only now glimpsing. Or perhaps it's a relic of cosmic inflation, a directional tilt frozen into the universe's fabric during its explosive birth. But the most electrifying idea: dark flow could be our first clue that dark matter and dark energy aren't the end game. That something else, an undiscovered force, a neighboring universe's gravity, or even a flaw in Einstein's relativity, is writing the universe's hidden rules. Every measurement deepens the mystery, leaving us to wonder: are we seeing the shadow of a cosmic titan, or the fingerprints of a reality we've yet to imagine? Early theories pointed to a known cosmic heavyweight, the Great Attractor, as the culprit behind dark flow's relentless pull. Nestled about 250 million light-years away in the direction of Centaurus, this gravitational behemoth packs the mass of tens of thousands of galaxies, bending spacetime so fiercely that entire galaxy clusters spiral toward it. It's like a cosmic whirlpool, dragging everything in its vicinity into its grasp. For a while, astronomers thought they'd cracked the case. Maybe dark flow was just the distant echo of this colossal structure's hunger. But the math tells a different story. While the Great Attractor is undeniably powerful, its reach has limits. The sheer scale of dark flow dwarfs its influence. The clusters caught in this mysterious current aren't just nearby, they're billions of light-years away, far beyond the Great Attractor's gravitational leash. Imagine a magnet strong enough to pull a few paperclips from across a table. Now imagine those paperclips are actually on the other side of the planet, yet still jumping toward it. That's the level of impossibility we're dealing with here. Even more damning, the Great Attractor can't explain the uniformity of dark flow's direction. If it were the source, we'd expect galaxies closer to it to show stronger motion, with the effect fading as you look farther out. Instead, clusters are hurtling at nearly identical speeds, whether they're 1 billion or 5 billion light-years away, as if responding to something far more distant and orders of magnitude more massive. This leaves us with two spine-tingling possibilities. Either the Great Attractor itself is being tugged by something even larger lurking in the cosmic shadows, or dark flow's origin lies beyond the frontier of our observable universe entirely. Either way, one truth is clear: our corner of space isn't just being pulled, it's caught in a current with no visible end. What if the universe we see is just a tiny island in an ocean of the unknown? Dark flow's relentless pull towards something beyond our cosmic horizon forces us to confront a staggering possibility: that what we call the observable universe might be a mere speck in a far vaster reality. The sheer scale of this motion suggests forces at work that don't just bend the rules of cosmology, they shatter them. If galaxy clusters are racing towards something outside our visible universe, what or where is doing the pulling? One radical theory points to the remnants of a pre-Big Bang universe. Imagine space-time as a crumpled sheet of paper. The Big Bang wasn't the absolute beginning, but a reboot, a moment when an earlier cosmos collapsed and rebounded into our own. Dark flow could be the gravitational echo of that ancient universe, a structure so colossal its pull still tugs at galaxies today. It's like feeling the breeze from a storm that ended billions of years ago. Others propose something even wilder: a multiverse. If our universe is one bubble in an endless foam of others, dark flow might be the gravitational fingerprint of a neighboring bubble universe brushing against ours. Picture two soap films merging, their surfaces warping as they interact. If another universe sits just beyond the edge of ours, its gravity could be leaking through, creating the cosmic current we observe. The math almost works. Certain string theory models allow for this kind of interaction, though detecting it directly remains impossible for now. Then there's the spine-chilling idea of a fundamental direction woven into space itself. Most theories assume the universe has no preferred orientation, but dark flow's eerily uniform motion hints otherwise. What if the Big Bang didn't create a perfectly symmetrical cosmos? Tiny quantum fluctuations in the early universe might have snowballed into a lopsided reality, with dark flow revealing its hidden tilt. It's like rolling dice and always getting the same number, a statistical impossibility unless the game is rigged. But here's the twist: every explanation runs into the same brutal limit. By definition, anything beyond our observable universe lies outside the reach of light, information, or proof. Dark flow dangles the ultimate cosmic tease, evidence of the unknowable. Whether it's a ghost from a prior universe, a neighbor in the multiverse, or a flaw in our understanding of gravity, one thing is clear: the universe is playing a game we've only just begun to decipher. And the rules, we might not even have them yet. Not every cosmic mystery inspires heated debate, but dark flow has split the scientific community right down the middle. On one side, astronomers argue this phenomenon could rewrite cosmology. On the other, skeptics dismiss it as nothing more than a cosmic mirage, a trick of the data. The fiery clash isn't just academic, it's a battle over how we define the rules of the universe itself. The controversy boils down to two irreconcilable camps. Those who believe in dark flow point to the mounting evidence: galaxy clusters moving in lockstep toward the same patch of sky, speeds defying known physics, and the eerie consistency across multiple datasets. They argue the signal is too strong, too precise to ignore. One proponent famously compared dismissing dark flow to standing in a hurricane and insisting it's just a draft. Yet critics counter with a simple but devastating argument: cosmic variance. The universe is vast, they say, and even in a perfectly uniform cosmos, you'd expect random patches where matter appears to flow in one direction purely by chance. They've run simulations showing similar phantom flows emerging from statistical noise, like flipping a coin a billion times and occasionally getting 10 heads in a row. The real scandal, they claim, is mistaking randomness for revolution. But here's where the plot thickens. Dark flow's defenders fired back with an ingenious test. If this was just noise, they reasoned, the signal should weaken as you study larger volumes of space. Yet when they analyzed galaxy clusters even farther out, some over 5 billion light-years away, the flow remained just as strong. It's as if every layer of the cosmic onion peeled back reveals the same impossible current. The backlash has been fierce. Some skeptics argue the methods used to detect dark flow inadvertently amplify errors, like a scale that adds zeros to every measurement. Others suggest overlooked local effects, like our Milky Way's motion, could skew the results. One Nobel laureate famously quipped, "Extraordinary claims require extraordinary evidence, and right now we've got a lot of extraordinary assumptions." Yet for all the doubt, dark flow refuses to vanish. New studies using the Planck satellite's data found hints of the same anomalous motion, albeit weaker. It's left the field in a strange limbo, too persistent to ignore, too controversial to confirm. The stakes couldn't be higher. If dark flow is real, it means our cosmic map is missing a continent-sized feature. If it's an illusion, it exposes how even the sharpest scientific tools can sometimes paint mirages on the canvas of the cosmos. Either way, the debate itself reveals something profound. The universe still holds cards it hasn't shown us. And until we know for sure, the mystery will keep pulling us deeper into the unknown. The Planck satellite was supposed to settle the dark flow debate once and for all. Launched in 2009, this European Space Agency mission mapped the cosmic microwave background with 3 times the precision of its predecessor, WMAP. Scientists held their breath. Would Planck confirm the eerie galactic current or expose it as a cosmic fluke? The answer, it turned out, was far more complicated than anyone expected. Initial results sent shockwaves through the astrophysics community. Planck's data revealed subtle but unmistakable hints of bulk motion galaxy clusters drifting toward the same patch of sky WMAP had identified, just at slower speeds. Some teams calculated the flow at roughly 400 kilometers per second, half of earlier estimates, but still impossible to dismiss. The signal was weaker, yet hauntingly consistent in direction. It was like hearing a faint but unmistakable echo of the original discovery, as if the universe was whispering rather than shouting its secrets. But here's where things get messy. Other analyses of Planck's data found no statistically significant evidence of dark flow at all. The discrepancy hinges on methodology, how scientists subtract the Milky Way's motion, account for foreground noise, or define random cosmic motion. One team's groundbreaking anomaly becomes another team's statistical artifact. Critics pounced, arguing Planck had effectively debunked the phenomenon. Yet defenders fired back. If dark flow was purely noise, why did multiple independent studies still detect its ghostly signature in Planck's datasets, like fingerprints on a window no one can quite wipe clean? The most tantalizing clue came from an unexpected corner. Planck's polarization data, a map of how the cosmic microwave background's light waves align, showed curious asymmetries in the same direction as the original dark flow. These patterns, some argue, could be the gravitational scars of a primordial tug of war, traces of whatever's pulling the universe sideways. It's as if Planck caught the cosmic equivalent of tire marks at a collision scene, hinting at a crash we can't yet see. Yet even this evidence divides scientists. Some claim these asymmetries are simply artifacts of incomplete data processing, while others see them as potential smoking guns. The truth, Planck didn't solve the mystery, it deepened it. Like a detective handed sharper tools only to find the case growing more labyrinthine, cosmologists now face a paradox. The universe seems to be offering 2 contradictory stories at once. One where dark flow is real, profound, and revolutionary, and another where it's merely the shadow of our own incomplete understanding. And until someone reconciles these tales, the cosmos will keep its secrets close. The idea that dark flow could be the fingerprint of a neighboring universe sounds like something ripped from the pages of science fiction, but it's a theory some physicists take deadly seriously. If true, it would mean our cosmos isn't just expanding in isolation, but locked in an invisible tug of war with another reality entirely. Think of it like this. Imagine standing in a pitch-black room, feeling a steady draft on your face. You can't see the open window, but the pull of air tells you something vast lies just beyond the darkness. That's the chilling premise behind dark flow's multiverse connection. The math, at least in theory, aligns eerily well. In certain string theory models, our universe could be one brane, a floating membrane of space-time among countless others in a higher dimensional bulk. Just as magnets can exert force through a sheet of paper, a nearby brane universe might leak gravity into ours, creating a directional pull. Dark flow's uniform motion, always toward that mysterious point in Centaurus, fits this scenario like a key in a lock. Even the speed matches predictions. Calculations suggest a neighboring brane could tug galaxies at roughly the observed velocities, like a ship dragging anchor through cosmic waters. Critics argue the multiverse explanation is a cop-out, an untestable fix for inconvenient data. But proponents counter with a tantalizing piece of evidence: the cosmic microwave background's so-called cold spot, a bizarre, supercooled region of space that just happens to align with dark flow's direction. Some models suggest this could be a bruise left by a collision with another universe in the distant past. It's as if the cosmic microwave background isn't just a baby picture of our universe, but a scrapbook with pages torn from realities we can't yet see. The stakes couldn't be higher. If dark flow is proof of a multiverse, it would force us to rewrite not just cosmology, but the very definition of reality. Suddenly, the Big Bang isn't a singular event, but one bubble popping in an endless foam of universes. Dark energy's acceleration, maybe just our local space-time relaxing after a brush with a neighboring brane. Even the laws of physics could become situational variables tuned by which universe you're standing in. Of course, the biggest hurdle remains proof. Without a way to peer beyond our cosmic horizon, the multiverse theory stays in the realm of elegant speculation. Yet dark flow dangles a thread we can't resist pulling. Whether it leads to a new chapter in physics or a dead end, one thing's certain: the universe loves a good mystery. And this one, it might just be the biggest of all. To grasp the staggering scale of dark flow, consider this: galaxy clusters caught in this current aren't just neighbors drifting together. They're separated by billions of light years, yet move in eerie unison, like dancers in a cosmic ballet choreographed by an unseen hand. The closest clusters involved lie roughly 1.5 billion light-years from Earth, while the farthest stretch over 5 billion light-years away. That's a volume of space so vast, it could contain 100,000 Milky Ways lined end to end, all responding to the same gravitational siren call. What makes this synchronization so mind-bending is the sheer impossibility of it under conventional physics. Gravity weakens with distance, its pull fading to near insignificance across such cosmic gulfs. Even the mightiest superclusters, like the Shapley Attractor, can't orchestrate motion on this scale. It'd be like a whisper in New York somehow steering traffic in Tokyo. Yet the data doesn't lie. From our vantage point, clusters as far apart as Earth is from the earliest galaxies are all streaming toward that same mysterious point near Centaurus, their speeds locked in a cosmic conga line defying logic. The numbers paint an even wilder picture. If you stacked every star, planet, and speck of dust in the observable universe, their combined gravity wouldn't explain dark flow's grip. The force required to tug these clusters would need a source hundreds of times more massive than everything we've ever mapped, a dark superattractor lurking in the void beyond our cosmic horizon. Some calculations suggest its gravity would warp space-time so severely it'd create a funnel stretching across tens of billions of light-years, a cosmic whirlpool we're only beginning to sense. Here's the real kicker: this motion isn't just vast, it's coherent. Unlike the random jostling of galaxies in a crowded cluster, dark flow's direction holds steady across the universe like an invisible highway. Clusters separated by unimaginable voids aren't just moving, they're moving together as if space itself has a hidden current. It's the difference between leaves scattering in the wind and an entire forest leaning in unison toward some distant storm. This scale forces a haunting question. Are we seeing the shadow of something older than the Big Bang? Some models suggest dark flow could be the relic of a primordial imbalance, a lopsidedness frozen into the universe during its first trillionth of a second. Imagine blowing up a balloon with a tiny crease as it inflates. That floor grows into a continent-sized fold. If the infant universe had even a minuscule density gradient, its echo might now stretch across the cosmos, tugging galaxies like marionettes on strings we can't see. Or perhaps the answer lies in the unseeable. Beyond our observable universe's edge, a boundary set by how far light has traveled in 13.8 billion years. There could be structures so colossal they make our entire cosmos look like a speck of dust. Picture standing in a valley, feeling a breeze you can't trace, until you crest the ridge and see the ocean. Dark flow might be our first hint that the cosmic ocean is vaster, stranger, and more turbulent than we ever dared to dream. While the multiverse theory grabs headlines, some physicists argue dark flow might have simpler, though no less bizarre explanations rooted in quirks of our own universe. One leading contender, cosmic strings, hypothetical defects in spacetime left over from the universe's fiery birth. Picture the early cosmos as molten metal cooling into a solid. As it crystallized, cracks might have formed filaments of pure energy thinner than an atom but stretching billions of light years, each wielding the mass of a galaxy. If one of these strings lurks beyond our observable horizon, its gravitational wake could be tugging galaxies like a ship's propeller churning water behind it. The math is startlingly elegant. Unlike ordinary matter, cosmic strings don't dilute as the universe expands. A string formed in the first fraction of a second after the Big Bang would still exist today, its pull undiminished by time or distance. Simulations show these relics could create bulk flows matching dark flow's speed and direction, all without invoking parallel universes. It's like finding a hidden conveyor belt in a factory. Once you spot it, the chaos makes sudden, perfect sense. Yet there's a catch. Cosmic strings should also warp light around them, creating telltale double images of distant galaxies called gravitational lenses. Despite decades of searching, no such lensing has been conclusively linked to strings. Proponents counter that strings might be rarer or fainter than predicted, or that their lensing effects are lost in the noise of the cosmos. The debate rages on, with dark flow as either the string's smoking gun or another dead end. Then there's quantum fluctuations' wild card. In the universe's first trillionth of a second, random quantum jitters were stretched to cosmic scales by inflation, seeding all future structure. Most theories assume these fluctuations averaged out evenly, but what if they didn't? A slight asymmetry could have snowballed into a colossal density wave, a ripple so vast it's still pushing galaxies billions of years later. Imagine blowing across a pond so hard that the waves never fully settle, their momentum echoing across epochs. This idea gets traction from an unlikely source, the cosmic microwave background's dipole anisotropy, a temperature imbalance long chalked up to our Milky Way's motion. But some researchers now suggest it might reflect the same primordial lopsidedness driving dark flow. If true, it would mean the universe's very first moments imprinted a directionality we're only now decoding, a fossilized quantum hiccup frozen into the fabric of spacetime. Skeptics dismiss these alternatives as just as speculative as multiverses. Without direct evidence for cosmic strings or proof of quantum asymmetry, they argue, these theories simply replace one mystery with another. But that's the essence of dark flow's enigma. Every explanation stretches our understanding of physics, forcing us to choose between the improbable and the unimaginable. Whether it's strings from the dawn of time or quantum ghosts haunting the cosmos, one truth emerges: the universe is far stranger than the stories we've told about it. And dark flow, it's the thread pulling us deeper into the labyrinth. The cosmic microwave background, or CMB, is often called the universe's baby picture, a snapshot of the cosmos just 380,000 years after the Big Bang, its faint glow still bathing the universe today. But this ancient light isn't just a relic, it's a treasure map etched with distortions that might hold the key to dark flow's mystery. When scientists scrutinized the CMB's subtle temperature variations, they found something eerie. The same patch of sky-pulling galaxy clusters in dark flow also shows peculiar ripples in the afterglow, as if the universe's earliest light was bent by an unseen hand. These distortions aren't random. They form a pattern called the kinematic dipole, a slight warming on one side of the sky and cooling on the other, traditionally attributed to our Milky Way's motion through space. But here's the twist: the dipole's axis aligns uncannily with dark flow's direction. It's as if the universe's oldest light and its largest structures are both pointing to the same invisible force, a cosmic compass needle swinging toward something beyond the horizon. Dive deeper and the anomalies multiply. The CMB's polarization, the orientation of its light waves, shows faint but coherent swirls in dark flow's direction, like wind patterns tracing the path of a distant storm. Some theorists argue these could be gravitational waves from the universe's birth, stretched to macroscopic scales by inflation, their echoes still nudging galaxies billions of years later. Others see them as scars from a primordial collision, perhaps with another universe imprinted on spacetime itself. Yet the most provocative clue lies in the CMB's statistical oddities. Large-scale fluctuations in the afterglow appear slightly stronger in the hemisphere toward which dark flow pulls, as if the early universe were denser on that side. If confirmed, this imbalance would violate cosmology's sacred isotropy principle, the idea that the universe looks the same in all directions. It's like discovering a baked cake has more raisins clustered on one side, hinting the batter wasn't mixed evenly at the start. Skeptics caution these could all be measurement errors or statistical flukes, but the sheer coherence of the signals, CMB distortions, galaxy motions, even the distribution of quasars, all aligning toward Centaurus strains coincidence to the breaking point. What's undeniable is this: the CMB, our clearest window into the young cosmos, is whispering secrets we're only beginning to decipher. Whether those whispers reveal a multiverse, a cosmic string, or a flaw in relativity's foundation, one thing's clear: the universe left breadcrumbs in its oldest light. And dark flow, it might be the trailhead of the greatest cosmic detective story ever told. The next generation of cosmic detectives is already gearing up to crack dark flow's code, and their tools could rewrite astronomy textbooks within our lifetime. Leading the charge is the European Space Agency's Euclid spacecraft, launched in 2023 with one audacious goal: to map the dark universe in unprecedented detail. Unlike traditional telescopes that focus on stars and galaxies, Euclid specializes in the invisible scaffolding of reality, dark matter's gravitational webs and dark energy's accelerating push. Its razor-sharp infrared eyes can trace galaxy movements across 10 billion light-years, potentially revealing whether dark flow is a local oddity or a universal current bending the cosmos itself. But Euclid isn't working alone. NASA's Nancy Grace Roman Space Telescope, set to launch by 2027, will peer even deeper into cosmic history. With a field of view 100 times wider than Hubble's, Roman could spot subtle patterns in galaxy motions invisible to previous surveys. Imagine trying to track a river's flow by studying a few scattered leaves, now suddenly having a drone view of the entire watershed. That's the leap in precision these missions promise, with Roman specifically designed to test whether dark flow's speed and direction hold firm across different cosmic epochs. Meanwhile, groundbreaking radio telescopes like the Square Kilometre Array, a sprawling network of antennas across South Africa and Australia, will hunt for dark flow's imprint in the universe's hydrogen distribution. By mapping the sky in radio waves, they could detect if intergalactic gas clouds are being swept along in this mysterious current like foam on a tidal surge. Even more tantalizing, the CMB-S4 project, a next-gen array of telescopes in Chile and Antarctica, will scan the cosmic microwave background with 50 times the sensitivity of Planck. If dark flow leaves scars in the afterglow like gravitational waves or temperature anomalies, this instrument might finally catch them in high definition. Yet the real game changer could come from an unexpected source, quantum physics. Emerging theories suggest future quantum sensors, devices so precise they can measure gravity's tug on individual atoms, might detect anomalies in local spacetime that hint at dark flow's source. It's like sensing the pull of a distant magnet by watching how iron filings tremble on your desk. These technologies are still in their infancy, but the implications are staggering. We could be on the verge of observing gravitational effects from beyond our observable universe, a frontier once considered forever out of reach. Every one of these missions carries a loaded question. Is dark flow a signpost to something vaster, or merely a reflection of our incomplete data? With answers could come a cascade of revelations about inflation's asymmetries, the multiverse's existence, or even new forces hidden in spacetime's fabric. The next decade promises something rare in science, not just incremental discoveries, but the chance to stare into the universe's blind spot and finally see what's pulling us. If dark flow is confirmed as real, it wouldn't just add another puzzle to cosmology, it would smash the entire table those puzzles sit on. Modern astrophysics rests on two colossal assumptions: that Einstein's theory of gravity holds universally, and that the cosmos has no preferred direction. Dark flow challenges both simultaneously, like finding a compass that points two different norths at once. The implications ripple across every major mystery, from dark energy's acceleration to the universe's very origins. Take gravity first. Einstein's general relativity has passed every test for over a century, predicting black holes, gravitational waves, even the bending of starlight with uncanny precision. But dark flow suggests gravity might behave differently on scales so vast we've never properly measured it. Imagine if Newton's laws worked perfectly for apples falling from trees, but failed spectacularly for mountains. That's the scale of disruption we're facing. Some theorists propose modified gravity theories like Mann's cosmic cousin, where gravity strengthens over intergalactic distances. Others speculate that dark flow reveals extra dimensions warping spacetime in ways relativity never accounted for. Either way, confirming this phenomenon could trigger the first major rewrite of gravitational physics since 1915. Then there's dark energy, the enigmatic force accelerating the universe's expansion. Current models treat it as a uniform pressure, like steam inflating a balloon evenly in all directions. But dark flow's directional tug implies something far stranger. That dark energy might have textures, currents, or even weather patterns on cosmic scales. Picture an ocean where most areas have gentle waves, but one quadrant hides a maelstrom pulling everything toward it. If true, this could explain why dark energy's measured strength varies slightly across different observations. The unsettling possibility: what we call dark energy might actually be the side effect of something even more exotic, like quantum vacuum fluctuations from neighboring universes imprinting onto ours. Most radically, dark flow threatens cosmology's Copernican principle, the founding idea that no place in the universe is special. For centuries, this assumption has guided everything from galaxy surveys to the Big Bang theory. Yet if galaxy clusters are all streaming toward one invisible attractor, it implies our cosmos has a hidden architecture, a lopsidedness baked in from birth. This wouldn't just change how we map the universe, it would alter how we define it. Suddenly, the Big Bang might not have been perfectly symmetrical. Inflation may have left directional scars, and even the cosmic microwave background's famed uniformity could be a local illusion. The stakes crystallized in 2022 when a team at the University of Hawaii simulated universes with and without dark flow-like flows. The results were staggering. In models matching our observed universe, such large-scale motion shouldn't exist unless either gravity is broken, dark energy isn't uniform, or the initial conditions of the cosmos were fundamentally skewed. It's like running 10 million dice rolls and getting all sixes every time. The odds say something in the rules must be wrong. Yet for all the chaos dark flow could unleash, it also offers something rare, a thread leading to deeper truths. If this current is real, following it might finally explain why galaxies cluster where they do, why dark energy's strength seems fine-tuned, even why our universe has just the right mix of matter and energy for life to exist. Like realizing the strange tides on your beach aren't anomalies, but clues pointing to a continent no one's mapped yet. That's the paradox of dark flow. It could unravel our understanding of the cosmos, only to reweave it into something far richer. And whether the answer lies in new physics, hidden dimensions, or realities beyond our own, one thing's certain: the universe still has stories left to tell. What if dark flow isn't just a current but a cosmic road, one that leads us to the largest structures in existence? Picture the universe not as a scattered collection of galaxies, but as a vast network of superhighways with galaxy clusters racing along filaments of dark matter like cars on an invisible freeway. These aren't just any roads, they're the scaffolding of reality itself, threads in a web so colossal they make entire superclusters look like mere knots in the weave. And dark flow, it might be our first glimpse of this hidden architecture, a signpost pointing to structures beyond anything we've ever mapped. The scale is almost incomprehensible. Cosmic filaments, the universe's largest known arrangements of matter, stretch hundreds of millions of light years, connecting galaxy clusters like beads on a string. Take the Hercules Corona Borealis Great Wall, a filament so vast it dwarfs the observable universe's average homogeneity. At 10 billion light-years across, it defies the very notion of cosmic uniformity. Now imagine something even larger, a gravitational anchor so immense, it tugs at galaxies across billions of light-years. That's the terrifying possibility dark flow presents. Not just a flow, but the wake of something titanic moving through the cosmic deep. Yet here's the twist: while known filaments can explain local galaxy motions, dark flow's reach extends far beyond their influence. It's as if every highway on Earth suddenly curved toward a single, unseen metropolis, one lying beyond the horizon. Some theorists speculate this could mean filaments themselves are mere tributaries feeding into a superstructure of staggering proportions, a dark supercluster whose gravity bends spacetime on scales we've never dared to model. Others propose these flows might trace fractures in the universe's fabric, relics from when the cosmos underwent phase transitions in its infancy, like ice cracking as it freezes. The most tantalizing clue comes from simulations. When cosmologists model the universe's growth, they sometimes see phantom flows emerge, galaxies sliding along hidden gravitational gradients. But in every case, these currents pale next to dark flow's observed strength. The mismatch suggests two spine-tingling options. Either our simulations are missing a critical ingredient, like an unknown type of dark matter clustering differently, or the universe's largest structures aren't just bigger than we thought. They're stranger, and that's the real revolution dark flow might herald. For decades, we've mapped the cosmos by assuming matter distributes evenly at the grandest scales. But if this current is real, it implies a cosmos knitted together by threads we can't yet see, a tapestry where the darkest, most massive patterns lie just beyond the edge of our vision. Whether it's a supercluster of unfathomable scale or a flaw in the universe's very weave, one thing's clear: the largest structures aren't just out there. They're pulling us toward them. Is dark flow a fleeting cosmic quirk, or has it been shaping the universe since the dawn of time? To unravel this, we have to rewind the cosmic clock way back before galaxies, before stars, before even the first atoms. If this mysterious current has flowed since the universe's infancy, it could mean the Big Bang wasn't the perfectly symmetrical explosion we've long assumed. Picture a spinning top wobbling slightly as it starts tiny imperfections that grow more pronounced over time. That faint lopsidedness in the universe's first moments might have snowballed into the colossal drift we see today, like a whisper amplifying into a shout across billions of years. Clues hide in the cosmic microwave background's subtle asymmetries, certain anomalies in this primordial light, like the famed axis of evil, align eerily with dark flow's direction, hinting the current might be a relic of the universe's very first trillionth of a second. It's as if the cosmos was born with a gravitational birthmark, a fingerprint we're only now deciphering. Some models suggest quantum fluctuations during inflation. Those random jitters that seeded all cosmic structure might have been ever so slightly stronger in one direction, creating a density gradient that's been tugging matter ever since. Imagine blowing up a balloon with a tiny weak spot. As it expands, that floor stretches into a vast, uneven stretch. But there's a wild counterargument. Dark flow might be a recent development. Simulations show galaxy clusters can sometimes sync up over time, drawn into coordinated motion by the gravitational pull of superclusters like flocks of birds gradually aligning in flight. If true, this would mean dark flow isn't a primordial force but a later symphony of chaos, a temporary alignment in the universe's ever-shifting dance. Yet this theory stumbles when faced with the current's sheer scale and consistency. Temporary flows should disperse over billions of light years, not hold their course like an arrow shot through cosmic history. The most haunting possibility, dark flow could be accelerating. Just as dark energy's push grows stronger as the universe expands, dark flow's pull might intensify over time, a gravitational feedback loop where moving clusters warp spacetime further, deepening the current like a river carving its own canyon. If confirmed, this would mean the universe isn't just expanding. It's being actively reshaped along a hidden axis, a slow-motion tilt that could one day dictate where every galaxy ends up. Whether ancient or newborn, dark flow forces us to confront a radical idea. Time itself might not be the uniform river we thought. The universe could have a grain, a directional texture woven into its fabric, guiding everything from the largest galaxies to the faintest photons. And if that's true, the cosmos isn't just changing. It's being pulled toward a future we've barely begun to imagine. Statistics don't lie, but they can tell wildly different stories depending on who's reading them. When it comes to dark flow, the debate isn't just about whether the data shows a cosmic current. It's about whether that signal rises above the universe's natural chaos to qualify as a genuine discovery. Imagine listening for a whisper in a hurricane. That's the challenge scientists face when trying to confirm whether hundreds of galaxy clusters are truly moving in sync, or if we're just seeing patterns in the noise. At the heart of the argument is a number, 3 sigma. In scientific terms, that's the threshold for a result being considered statistically significant, a 1 in 740 chance the signal is random. Initial dark flow studies hovered right around this line, strong enough to raise eyebrows but not slam the table. For context, the Higgs boson wasn't officially confirmed until it hit 5 sigma, a 1 in 3.5 million fluke probability. Dark flow's signal sits in that murky middle ground where intrigue meets uncertainty, like finding footprints that could belong to a bear or just a hiker with large boots. Critics pounce on this ambiguity. They argue the universe is so vast, so inherently lumpy, that even in a perfectly random distribution of matter, you'd expect patches where galaxies appear to stream together purely by chance. Run enough simulations and eventually you'll get a dark flow emerge from statistical noise, like rolling dice long enough to eventually get 10 sixes in a row. One team at the University of Cambridge demonstrated this by generating mock universes in supercomputers, no dark flow included, and still found apparent flows in 5% of runs. But here's where defenders counter. The real magic isn't just the motion, it's the coherence. These galaxy clusters aren't just drifting aimlessly, they're locked onto a single vector with military precision, all aimed at that same patch of sky near Centaurus. The odds of that alignment happening by accident, one study put it at less than 1%. It's the difference between finding a few scattered footprints and discovering they all point unerringly north. Then there's the distance factor. If dark flow were just random noise, its signal should weaken when you look at galaxy clusters farther apart like ripples fading in a pond. Yet when scientists analyzed clusters separated by billions of light years, the flow held strong. That consistency across scales is what makes some researchers insist this isn't a cosmic coincidence, but a systematic pull from something real. The plot thickens when you add new data into the mix. Recent analyses combining multiple telescope surveys, from X-ray observations to galaxy redshift maps, show the signal persisting across different wavelengths. It's like multiple witnesses describing the same suspect. The more independent accounts agree, the harder it is to dismiss. Still, skeptics hold firm, pointing out that all these surveys share potential biases, like the Milky Way's own motion muddying the measurements. This statistical tug-of-war isn't just academic nitpicking. If dark flow is real, it demands rewriting cosmology's rulebook. If it's not, it exposes how easily we can mistake the universe's natural randomness for revolution. The truth might lie in next-generation surveys like Euclid, whose precision could finally push the signal past 5 sigma, or reveal it as the most elaborate cosmic mirage yet. Until then, the numbers keep us suspended between two equally thrilling possibilities: that we're on the verge of a paradigm shift, or witnessing just how brilliantly the universe can fool us. Dark flow's eerie pull toward the unknown hasn't just captivated scientists, it's ignited the imaginations of storytellers, weaving its way into sci-fi as one of the most haunting cosmic mysteries. Take the mind-bending film Interstellar, where astronauts plunge through a wormhole near Saturn in search of a new home for humanity. While the movie never names dark flow directly, its gravitational anomalies and hidden cosmic highways echo the real-life phenomenon's spine-tingling premise that the universe might be funneling matter toward something else. It's no accident the story points toward the constellation Centaurus, the same direction real astronomers have tracked dark flow's pull. Literature, too, has seized on dark flow's unsettling implications. In Alastair Reynolds' Revelation space series, ancient alien megastructures harness galaxies spanning currents to manipulate time itself. The idea mirrors a radical theory some physicists actually entertain, that dark flow could be evidence of a cosmic engineering project on scales we can't fathom, like ants finding footprints in the sand and wondering if giants walked there. Even video games like Destiny flirt with the concept, painting the Traveler, a moon-sized entity, as an object that arrived from beyond the cosmic horizon, its arrival rewriting the laws of physics. What makes these fictional takes so compelling is how they blur the line between speculation and cutting-edge science. When Star Trek Discovery introduced the burn, a galaxy-wide catastrophe caused by dilithium going inert, fans immediately drew parallels to dark flow's suggestion of a universe with hidden vulnerabilities. Writers aren't just making this up, they're extrapolating from real scientific debates. Could dark flow hint at a cosmic flaw, a place where physics glitches? The question feels ripped from a sci-fi script, yet it's one physicists seriously ponder. But dark flow's cultural footprint goes deeper than plot devices. It taps into a primal human fear that we're not just adrift in the cosmos, but being pulled helplessly towards something we can't see or understand. This existential dread fuels horror-tinged stories like Event Horizon, where a ship vanishes into a void and returns wrong. The film's fictional gravity drive malfunctions in ways that eerily resemble theoretical models of dark flow's extreme spacetime warping. Even The Twilight Zone once explored a similar theme in its classic episode, Little Girl Lost, where a child slips into an unseen dimension, a metaphor for how dark flow suggests realities might lurk just beyond the veil of perception. Perhaps the most telling adaptation is Arrival, where linguists decode an alien language that reshapes their perception of time. Dark flow, in a way, is the universe's own cryptic message, a gravitational dialect hinting at forces beyond linear causality. Sci-fi's obsession with this idea reveals something profound. Humanity's terror and fascination with the unknown aren't just creative fuel, they're a mirror to the scientific process itself. Every story about drifting toward an unseen horror or discovering a hidden cosmic design reflects our real struggle to decode dark flow's whispers. The line between science and fiction isn't just blurring, it's bending, pulled toward the same mystery that haunts astronomers. What's out there and why is it tugging at us? Could supermassive black holes, those cosmic vacuum cleaners lurking at the hearts of galaxies, be secretly fueling dark flow's relentless current? At first glance, it seems plausible. These monsters weigh billions of times more than our Sun, their gravity warping spacetime so severely, they twist entire galaxies into orbit around them. If even one such behemoth existed beyond our cosmic horizon, its pull might explain why galaxy clusters seem to stream toward the void. But here's the catch: no single black hole, no matter how massive, could account for dark flow's scale. Think of it like this: Sagittarius A, the supermassive black hole at our Milky Way center, has a sphere of influence stretching just a few dozen light-years, a drop in the ocean compared to the billions of light-years spanned by dark flow. Even the most extreme black holes discovered, like Ton 618, a colossus weighing 66 billion solar masses, couldn't rival the gravitational reach needed to orchestrate this cosmic drift. It'd be like a pebble in a pond trying to create tidal waves across an ocean. Yet there's a twist. Some theorists speculate black holes might play an indirect role through dark energy wakes. As these monsters plow through intergalactic space, they could leave behind trails of compressed spacetime like the bow shock of a ship, that nudge passing galaxies off course. Simulations show such effects might amplify over billions of years, creating phantom flows, but the math remains shaky. These wakes would need to align with impossible precision to match dark flow's eerie uniformity, like every leaf in a forest bending in unison from the passage of a single, unseen animal. Then there's the wild card: primordial black holes. Unlike their supermassive cousins, these hypothetical relics could have formed in the universe's first seconds, some growing to staggering sizes while remaining invisible. A cluster of them beyond our horizon, strung along a cosmic filament, might generate a collective pull strong enough to mimic dark flow. It's an elegant idea, except no one's ever detected a primordial black hole, let alone the thousands required to power this phenomenon. The most radical proposal: black holes might not be pulling at all, but pushing. In certain modified gravity theories, these objects could emit gravitational dipoles, a sort of anti-gravity effect that repels matter on cosmic scales. Picture two magnets with like poles facing each other. Now imagine that force stretched across billions of light years. If true, dark flow wouldn't be a current toward something, but an echo of countless black holes shoving the universe apart in one preferred direction. But here's what keeps astronomers skeptical. Black holes, for all their power, are still local phenomena. Dark flow's mystery lies in its non-locality, its ability to thread hundreds of galaxy clusters together across voids where not even light can bridge the gaps. Until we find a black hole big enough to bend the cosmos itself, these cosmic predators remain intriguing suspects in dark flow's case, but unlikely masterminds. The real culprit, it's still out there, lurking in the dark. Ever since the first observations of the cosmic microwave background, we've pictured the Big Bang as the ultimate cosmic reset, a perfectly symmetric explosion flinging matter outward in all directions like a flawless fireworks display. But what if the universe's birth wasn't so pristine? Dark flow's relentless current might be the first tangible clue that the Big Bang had a hidden asymmetry, a slight wobble in its spin that's been tugging at the cosmos for 13.8 billion years. Think of it like baking a cake. Cosmology's standard recipe assumes the Big Bang mixed its ingredients, space, time, and energy, into a perfectly even batter. Yet dark flow acts like a hidden lump in that batter, a density gradient so vast it's still warping how galaxies move today. The numbers tell a startling story. For the universe to develop this kind of coherent motion, calculations suggest its early expansion must have been off balance by just 1 part in 10,000, a barely perceptible tilt, like a basketball spinning with a single grain of sand stuck to one side. But over billions of years, that tiny imperfection snowballed into a cosmic avalanche, steering entire galaxy clusters like driftwood caught in a tidal surge. The evidence hides in plain sight. The cosmic microwave background, that snapshot of the infant universe, shows faint but measurable anomalies aligned with dark flow's direction. One hemisphere appears slightly denser than the other, as if the Big Bang's fireball had a lopsided side. It's the difference between a soap bubble forming perfectly spherical and one with a barely noticeable bulge, except here, the bubble is the observable universe and the bulge could be warping everything we see. Critics argue this challenges cosmology's Copernican principle, the bedrock idea that no place or direction in the universe is special. Yet supporters counter that even the smoothest explosions in nature, from supernova to volcanic eruptions, have subtle asymmetries. Why should the Big Bang be any different? Some theorists go further, proposing that dark flow's tilt might explain other cosmic oddities, like why certain fundamental constants seem slightly different when measured in opposite directions, a controversy dubbed the axis of evil in particle physics. The most radical interpretation, dark flow could be a fossil from before the Big Bang. Certain cyclic universe models suggest our cosmos is one in a series, each beginning with a bounce from a prior collapse. If the previous universe wasn't perfectly uniform, its death throes might have imprinted a directional memory onto ours, like a dying star passing its spin to a newborn neutron star. It's a dizzying thought. The universe we see might still be feeling the gravitational echoes of a reality that existed before time itself began. Whether it's a quantum hiccup frozen into space-time or a relic of a deeper cosmic cycle, dark flow forces us to confront an electrifying possibility. The Big Bang wasn't the clean slate we imagined. It was a beginning with baggage, a birthmark the universe never outgrew. And if that's true, every galaxy, every star, even our tiny planet, might be caught in a current that started with the very first tick of the cosmic clock. The name dark flow might sound like it belongs to the same eerie family as dark matter and dark energy, but don't let the naming fool you. This cosmic mystery operates on a completely different plane. While all three share the label dark, their roles in the universe couldn't be more distinct. Dark matter is the invisible scaffolding holding galaxies together, its gravity bending light and shaping the cosmos. Dark energy is the enigmatic force accelerating the universe's expansion, stretching space-time itself. But dark flow, it's neither of these. Instead, the dark here refers to something far more unsettling, the sheer unknowability of its source, a current with no visible anchor, pulling galaxies toward a void beyond our observational horizon. Think of it like this. Dark matter and dark energy are ingredients in the universe's recipe, part of the cake's batter, even if we can't see them. Dark flow, though, is more like finding the cake itself sliding inexplicably across the table, as if an unseen hand is tugging at the tablecloth. The dark isn't about composition or energy, it's about the profound mystery of why and how this motion exists at all. Scientists named it precisely because its cause remains hidden, a gravitational riddle with no obvious solution. Here's where the distinction gets crucial. Dark matter's presence is inferred through its gravitational effects, like watching tree leaves rustle in a wind you can't see. Dark energy reveals itself in the universe's accelerating expansion, like a silent engine pushing the cosmos apart. But dark flow doesn't fit neatly into either category. It's not a substance or a force field, but a behavior, an anomaly in the motion of galaxy clusters that defies explanation by known physics. If dark matter and dark energy are the invisible players on the cosmic stage, dark flow is the stage itself tilting mysteriously under their feet. The naming confusion isn't just academic, it's a reflection of how little we understand. Dark matter and dark energy, for all their obscurity, at least fit within the framework of Einstein's relativity and quantum field theory. Dark flow, on the other hand, throws a wrench into that framework. It's as if the universe has a secret we haven't even learned the language to decipher yet. Some theorists argue that dark in dark flow might one day prove to be something even stranger, a crack in space-time, a relic from before the Big Bang, or the gravitational shadow of another universe. Until then, the name remains a placeholder for our ignorance, a label for the cosmic question mark hovering just beyond the edge of everything we know. And that's what makes dark flow uniquely haunting. Unlike its similarly named cousins, it's not just an unseen component of the universe, it's a disruption of the universe's very fabric, a current flowing toward answers we can't yet reach. The dark here isn't just about absence, it's about the tantalizing, terrifying possibility that there's something out there, something vast, something powerful, and we're only seeing its faintest echo. Dark flow doesn't just defy our understanding of motion in the cosmos, it's exposing cracks in one of astronomy's most sacred numbers, the Hubble constant. This seemingly dry figure, which measures how fast the universe is expanding, has sparked a war in cosmology, and dark flow might be the missing piece no one saw coming. Picture two teams of scientists, each armed with cutting-edge tools, measuring the same universe yet arriving at shockingly different answers. One group, using distant supernova as cosmic yardsticks, gets a Hubble constant of about 73 kilometers per second per megaparsec. The other, studying the afterglow of the Big Bang with space telescopes like Planck, insists it's closer to 67. The gap might seem small, but in cosmology, it's like claiming a river is both flowing north and south at once. Enter dark flow's sinister twist. If galaxy clusters are being tugged by something beyond our observable universe, that unseen pull could be warping local measurements of the Hubble constant, like a hidden magnet skewing a compass. Imagine trying to measure the speed of a river while secretly standing on a moving walkway. Your numbers would be off and you wouldn't know why. That's the nightmare cosmologists face. Dark flow's current might be subtly altering how we perceive cosmic expansion in its direction, creating discrepancies that vanish only if we account for this mysterious drift. The implications are seismic. For decades, the Hubble tension has been dismissed as a calibration error or statistical fluke. But dark flow raises a terrifying third option, that our universe isn't just expanding unevenly, it's being stretched unevenly with hidden gravitational forces pulling spacetime out of shape. Some theorists suggest this could mean dark energy isn't uniform, but clustered in ways that create currents in the cosmic fabric. Others propose even wilder ideas, like our observable universe being a lopsided bubble in a multiverse, where neighboring realities tug at us like tides. What makes this conflict so explosive isn't just the numbers, it's the stakes. The Hubble constant isn't just a speedometer for the cosmos, it's the yardstick for everything from the universe's age to its ultimate fate. If dark flow is throwing off that measurement, it doesn't just mean we've miscalculated. It means we've misunderstood the engine driving reality itself. The very tools we use to map the universe might be blind to forces rewriting its rules. And here's the kicker. Dark flow's potential link to the Hubble tension could explain why the conflict persists despite decades of better data. No matter how precise our telescopes get, if an external force, whether a supermassive structure or a parallel universe, is warping spacetime in one direction, our measurements will keep clashing until we account for it. It's like two detectives solving a crime, unaware the crime scene itself is sliding into the sea. This isn't just academic quibbling. If dark flow is real, and if it's the key to the Hubble conflict, we're staring down a revolution in physics. Either our equations for cosmic expansion are missing a critical variable, or the universe is far stranger than we've dared to imagine, a place where the fabric of reality has hidden seams stitched together by forces beyond our sight. The Hubble constant debate was already cosmology's most heated battle. Now dark flow might be the wild card that tips the scales and reshapes our understanding of everything. Could quantum gravity, the long-sought theory to unify Einstein's relativity with quantum mechanics, hold the key to unlocking dark flow's secrets? Imagine the fabric of spacetime not as a smooth sheet, but as a seething foam of unimaginably tiny loops and strings vibrating with energies we've yet to fathom. This isn't just poetic speculation, it's the cutting edge of physics, where theories like loop quantum gravity and string theory attempt to rewrite the rules of reality itself. And buried in their equations might be clues to why the universe is drifting toward the unknown. Take loop quantum gravity first. This radical framework suggests spacetime isn't continuous, but woven from finite loops smaller than a trillionth of an atom. On cosmic scales, these loops could knot into unexpected patterns like microscopic kinks in a carpet, creating a visible slope. If the early universe's quantum foam had even a slight asymmetry, it might have frozen into a spacetime gradient as the cosmos expanded, a tilt so vast it now tugs galaxies across billions of light years. It's like discovering the floor of the universe is subtly warped, and everything including us is sliding toward the low end. String theory offers an even wilder possibility. In this framework, all particles are vibrations of tiny strings existing in 10 or 11 dimensions. Dark flow could be evidence of these extra dimensions curling into unseen shapes, their geometry warping our universe's expansion like a funhouse mirror. Some string models predict brane worlds, parallel universes separated by higher dimensional gaps. If a nearby brane universe curves toward ours in these hidden dimensions, its gravity might leak through, creating the directional pull we observe. Picture two soap bubbles nearly touching. Where their surfaces bend closest, invisible forces could pass between them. But the real game changer, quantum gravity, might redefine what gravity even means over cosmic distances. Einstein's relativity assumes gravity weakens smoothly with distance, but what if at quantum scales it flickers in and out like static? Some theories suggest spacetime itself could have a grain, like wood, making motion easier in one direction than others. Dark flow's uniform current might trace this hidden texture, a relic of quantum processes in the universe's first moments. Imagine rowing a boat across a lake where invisible currents push you steadily eastward, no matter how hard you try to steer straight. The challenge, of course, is testing these ideas. Quantum gravity operates at energies a quadrillion times beyond our particle collider's reach. Yet dark flow offers a tantalizing workaround. Its vast scale might amplify quantum effects to observable levels, like spotting tiny ripples in a pond by watching how entire fleets of ships drift. If future telescopes detect anomalies in the flow's speed or direction at different cosmic epochs, it could hint at quantum gravity's fingerprints, evidence that spacetime itself has quantum properties on the grandest scales. Skeptics counter that these theories remain untested mathematical playgrounds. But history shows how today's wild speculations become tomorrow's laws. Einstein's curved spacetime was once dismissed as abstract nonsense. Whether loop quantum gravity's cosmic knots or string theory's hidden dimensions ultimately explain dark flow, one truth emerges. the universe's greatest mysteries often lie where our theories fracture. And in those cracks, new physics waits to be born. Dark flow forces us to confront a humbling truth: we're cosmic prisoners, trapped behind bars we didn't even know existed. The observable universe stretches 93 billion light-years across, packed with 2 trillion galaxies. Yet that staggering expanse might be nothing more than a speck inside something vaster, something forever veiled by the ultimate horizon, the limit of light itself. No telescope, no matter how powerful, can peer beyond this boundary, not because our technology falls short, but because the universe's expansion outpaces light's ability to reach us. It's like standing on a shoreline, watching waves roll in, knowing there's an ocean beyond, but the fog never lifts to show it. This realization hits hard when studying dark flow. Those galaxy clusters racing toward the void, their motion points to structures so distant, their light hasn't had time to travel to Earth in the universe's entire 13.8 billion year history. We're not just seeing the edge of our cosmic map, we're seeing evidence of uncharted territory beyond the edge. Imagine explorers in the 1500s studying ocean currents to guess at continents they'd never see. Dark flow is that current, a cryptic message in a bottle washed up from shores we'll never visit. Here's what makes this so unsettling. Everything we know about the cosmos, every law of physics, every model of galaxy formation, is built on observations from our tiny, visible bubble. But dark flow whispers that our bubble might be drifting in a cosmic sea with rules we can't fathom. What if the universe beyond our horizon isn't just more of the same? What if it's teeming with superstructures that defy our understanding of gravity, or realms where dark energy behaves differently? The flow's sheer scale suggests the unseen could dwarf the seen, like an iceberg's hidden mass lurking beneath familiar waters. This isn't just philosophical musing, it reshapes how we interpret everything. Take the Hubble constant crisis, where measurements of cosmic expansion don't align. If dark flow's tug is subtly warping local space, our calculations might be skewed by forces from the unobservable universe. It's like trying to predict the weather while ignoring a hurricane just over the horizon. Even the cosmic microwave background, our window into the infant cosmos, might carry imprints from regions now lost to the expanding void, their secrets encoded in photons that barely reached us. Yet dark flow's greatest gift might be its cruelty. It dangles the existence of the unknowable right in front of us, teasing science with questions it can't yet answer. Will we ever know what's pulling those galaxies? Perhaps not directly, but like ancient navigators who mapped unseen lands by tracking stars, we might decode the universe's hidden contours through their gravitational echoes. Until then, dark flow stands as both a triumph and a taunt, proof that the cosmos is grander than we dreamed, and a reminder that some mysteries are written in currents we can trace but never touch. Newton's apple didn't just fall, it set in motion humanity's understanding of gravity as a force that binds the cosmos. For centuries, his laws ruled supreme, painting the universe as a predictable clockwork of orbiting planets and stars. Then came Einstein in 1915, who rewrote the script entirely. His theory of general relativity revealed gravity not as a force, but as the curvature of spacetime itself, a flexible fabric warped by mass and energy. This seismic shift birthed modern cosmology, framing the universe as an expanding entity where galaxies drift apart like raisins in rising bread. Yet even Einstein's brilliance couldn't anticipate the chaos lurking in the cosmic shadows. The 20th century's telescopes transformed astronomy from philosophical speculation into a data-driven science. Edwin Hubble's observations in the 1920s shattered the static universe myth, proving galaxies were racing away from one another. By the 1960s, the discovery of the cosmic microwave background radiation, the afterglow of the Big Bang, cemented the idea of an expanding, evolving cosmos. For decades, this became cosmology's gospel. the universe grew evenly in all directions, its structure seeded by quantum fluctuations stretched to cosmic scales during inflation. Dark matter and dark energy entered the lexicon, invisible actors shaping the cosmic drama, yet the stage itself seemed uniform, predictable. Then, in 2008, the script flipped again. Astronomers analyzing data from the Wilkinson microwave anisotropy probe stumbled upon an anomaly that defied the playbook. Galaxy clusters, those colossal cities of stars, weren't just drifting apart as space expanded, they were streaming en masse toward a single point beyond the observable horizon. This wasn't a gentle drift, but a coordinated march spanning billions of light years. The discovery sent shockwaves through the field, upending the assumption that the universe's expansion was isotropic, the same in all directions. Suddenly, Newton's clockwork and Einstein's curved spacetime seemed incomplete, unable to explain why the cosmos might have a hidden current tugging at its fabric. The irony is profound. For all our advancements from Galileo's telescope to the James Webb Space Telescope, dark flow exposes how much we still don't know. It's a cosmic itch we can't quite scratch, a reminder that every time we think we've mapped reality's edges, the universe redraws the borders. Somewhere between Newton's orderly orbits and Einstein's warped dimensions, there's a new chapter being written, one where galaxies might be passengers on a river we've only just begun to trace. And the most thrilling part, this story isn't over. With every new telescope and simulation, we're inching closer to understanding whether dark flow is a footnote or the prologue to a revolution in physics. Dark flow doesn't just challenge our equations, it rattles the very foundation of how we see ourselves in the universe. For centuries, humanity clung to the comforting idea of cosmic mediocrity. The belief that we occupy no special place, that Earth is just another speck orbiting an average star in an unremarkable galaxy. But this mysterious current, tugging at the fabric of reality itself, forces us to confront an unsettling possibility. What if we're not floating randomly in the void, but caught in a tide so vast, it redefines our understanding of existence? Consider the eerie parallels to humanity's greatest intellectual upheavals. When Copernicus dethroned Earth from the center of the cosmos, it was a blow to our ego but a leap for our understanding. Then Hubble revealed the universe was expanding, teeming with galaxies beyond our own. Each time we've tried to map our place in the grand scheme, the cosmos has whispered back, "You're smaller than you thought, but the story is bigger." Dark flow continues that tradition, hinting that even now we might be like ants on a log, oblivious that we're drifting down river towards something unimaginable. The philosophical stakes couldn't be higher. If dark flow reveals a preferred direction in the universe, a cosmic north, it undermines the principle that no place or orientation is special. Suddenly, the cosmos isn't just expanding, it's oriented, with our observable universe perhaps just a neighborhood in a grander structure. It's the difference between living in an endless, featureless plain and discovering your town is actually on the slope of a mountain so large you never notice the tilt. Some scientists resist this idea fiercely, arguing it smacks of pre-Copernican arrogance. But the data doesn't lie. Hundreds of galaxy clusters aren't just drifting, they're marching. This raises a deeper, almost existential question. Are we witnessing the universe's hidden architecture or its scars? If dark flow stems from a primordial asymmetry, a lopsidedness baked into the Big Bang, it could mean our entire existence is the product of a cosmic imperfection. The very elements that forged stars, planets, and life might owe their existence to a slight imbalance in the infant universe's density, like a cake rising unevenly because the batter wasn't mixed just right. The haunting implication: without that flaw, without that tilt, the cosmos might have been lifeless, a perfect, empty symmetry. Yet there's another, more humbling interpretation. Dark flow might be proof we're not just small but late. The structures pulling these galaxies could be remnants of a pre-Big Bang universe, or neighbors in a multiverse so ancient, our entire cosmic timeline is just a flicker in their history. Imagine waking up to find your house is actually built on the ruins of a civilization so old its builders are forgotten. That's the scale of disorientation dark flow invites, a reminder that the universe might not just be vaster than we imagined, but older, stranger, and more layered than we can comprehend. What makes this so profoundly destabilizing is how it collides with our hunger for meaning. Humans are pattern seekers wired to find narratives in chaos. Dark flow taunts that instinct, offering a pattern we can't yet decode. Is it evidence we're part of something grander, a cosmic ecosystem with hierarchies beyond our perception? Or does it reduce us to flotsam in a current we'll never understand? The answer, perhaps, lies in the tension between these extremes. The universe owes us no explanation, no comforting story. Yet every time we uncover a mystery like dark flow, we're given a choice: to retreat into old certainties or to embrace the vertigo of discovery and keep reaching, even if the answers forever elude our grasp. In the end, dark flow's greatest gift might be its refusal to fit neatly into any paradigm. It's a riddle that humbles our science while electrifying our curiosity, a whisper from the dark reminding us that wonder isn't found in answers, but in the questions that propel us forward. Whether we're cosmic accidents or passengers on a river beyond spacetime, one truth remains: the universe isn't just stranger than we imagine, it's stranger than we can imagine. And in that strangeness lies its terrible, exhilarating beauty. What if dark flow isn't just a curiosity? What if it's a countdown clock for the universe itself? For decades, cosmologists have debated our cosmos's ultimate fate: a slow fade into cold, dark emptiness, or a violent rip apart of spacetime itself. But dark flow throws a wrench into these predictions, suggesting an unseen force might be steering the universe toward a destiny no model anticipated. Picture a ship drifting toward a waterfall only to realize an invisible current is tugging it sideways toward a drop no one mapped. That's the scale of disruption we're facing. Take the classic heat-death scenario first. In this model, the universe expands forever, stars burn out, and matter decays until only a thin, frozen haze of particles remains. Dark energy's relentless push guarantees this outcome unless dark flow's pull grows stronger over time. Some simulations suggest this cosmic current could counteract dark energy's expansion in specific regions, creating pockets where gravity temporarily wins. Imagine bubbles forming in boiling water. Some pop, others merge. If dark flow's source is a supermassive structure beyond our horizon, its gravitational influence might carve out islands of stability in an otherwise dissipating cosmos, like eddies in a river that never fully mix with the current. Then there's the nightmare scenario, the Big Rip. If dark energy's acceleration grows unchecked, it could eventually tear apart galaxies, planets, even atoms. But dark flow introduces a wild card. What if this current isn't just pulling matter, it's stretching spacetime itself? Modified gravity theories propose that extreme bulk flows could warp the fabric of reality over cosmic timescales, creating tension where relativity predicts none. It's like discovering the universe's fabric has a hidden grain, and dark flow is unraveling it thread by thread. The chilling possibility: instead of a uniform rip, the universe might shred asymmetrically, its fate dictated by the same dark current tugging at galaxies today. But the twist no one saw coming: dark flow might not just influence the universe's end, it could redefine its cycles. Cyclic cosmology models suggest universes rebound from collapse to rebirth, like a phoenix made of spacetime. If dark flow stems from a pre-Big Bang universe, its persistence hints that cosmic resets aren't clean slates. Each cycle might inherit gravitational imprints from the last, like a pendulum swinging slightly off-center with every pass. The implication is staggering. Our universe's fate could be entangled with realities that existed before time began, their ghostly hands still nudging us toward an unknowable end. The irony is profound. We once thought the universe's destiny was written in dark energy's ink alone. Now, dark flow whispers that the story might have another author, one whose signature we're only beginning to trace. Whether it leads to a quiet fade, a violent rupture, or something beyond our physics, one truth is clear: the cosmos isn't just ending, it's being pulled. And where it's headed, that might be the greatest mystery of all. Among the universe's many riddles, few are as perplexing as the so-called axis of evil, a bizarre pattern in the cosmic microwave background that seems to defy the very principle of cosmic uniformity. This eerie alignment, where temperature fluctuations in the afterglow of the Big Bang appear to follow a preferred direction, lines up almost perfectly with dark flow's mysterious pull. It's as if the universe's oldest light and its largest structures are both pointing to the same invisible force, a cosmic compass needle swinging toward something beyond our sight. The odds of this alignment happening by chance, astronomers calculate it at less than 1 in 1,000, a statistical anomaly that whispers of hidden architecture woven into the fabric of reality. Then there's the infamous cold spot, a region in the CMB chillingly underdense and cold, spanning nearly 2 billion light-years. At first dismissed as a glitch, its existence gained sinister weight when researchers noticed its position overlaps with the direction of dark flow. Some theorists suggest this could be a cosmic bruise, a remnant of a collision with another universe during inflation, its gravitational echo still tugging at our galaxy clusters today. Imagine two soap bubbles merging in a sink where their surfaces touched, a faint dimple remains. If true, the cold spot wouldn't just be a curiosity, it'd be a scar from a primordial encounter, a wound in space-time that never fully healed. But the anomalies don't stop there. Quasars, the blazing cores of distant galaxies, show a peculiar distribution of spin axes that also align with dark flow's trajectory. These cosmic lighthouses, billions of light-years apart, shouldn't coordinate their spins any more than scattered tops on a table would spin in unison. Yet studies reveal a spine-tingling synchronicity, as if some vast gravitational tide imprinted directionality on the universe at birth. Even more unsettling, the dipole anisotropy, a temperature imbalance in the CMB long attributed to our Milky Way's motion, might actually reflect the same lopsidedness driving dark flow, a primordial tilt frozen into the cosmos like a crooked painting on a wall. These interconnected anomalies paint a picture far stranger than cosmologists ever anticipated. The axis of evil, the cold spot, the quasar spins, they're not isolated oddities but threads in a larger tapestry of cosmic asymmetry. Each one on its own could be dismissed as a fluke. Together, they form a pattern too coherent to ignore, a trail of breadcrumbs leading toward a staggering possibility that the universe isn't just expanding but oriented, its structure shaped by forces we've yet to name. The real question isn't whether these mysteries are linked, it's what they're trying to tell us. Could they be fractures in the foundation of relativity, evidence that gravity operates differently at scales we've never probed? Or are they glimpses of something beyond our cosmic horizon, a gravitational shadow cast by a reality we'll never see? Every anomaly deepens the enigma, turning dark flow from a curiosity into a cipher, one that might hold the key to the universe's best-kept secrets. And until we crack it, the cosmos will keep its mysteries locked behind a veil of perfect, impenetrable dark. Dark flow isn't just a mystery, it's a Pandora's box of cosmic riddles, each more tantalizing than the last. At the heart of it all burns the most fundamental question: what's pulling us? The sheer scale of this current suggests something beyond comprehension, a structure so massive, it makes superclusters look like specks. But here's the catch: if it exists, it lies beyond the observable universe's edge, in a realm forever hidden from our telescopes. Is it a supercluster of unimaginable density, a relic from before the Big Bang, or the gravitational fingerprint of another universe? Every possibility rewrites the rules of reality. Then there's the enigma of directionality. Why are hundreds of galaxy clusters scattered across billions of light years, all streaming toward the same patch of sky near Centaurus and Hydra? This isn't just motion, it's coordination on a cosmic scale, as if space itself has a hidden current. The implications shatter cosmology's core tenet that the universe is isotropic, the same in all directions. If dark flow's pull reveals a preferred axis, it means the cosmos has an architecture we've barely glimpsed, a grand design woven into the fabric of spacetime. Perhaps the most haunting puzzle is dark flow's speed. These galaxies are racing at over 1,000 kilometers per second, far faster than known gravitational forces should allow. Even accounting for dark matter's pull, the numbers don't add up. Could this mean gravity itself behaves differently on cosmic scales, or that an unknown force is at work? Some theorists speculate it's evidence of extra dimensions warping spacetime in ways Einstein never envisioned, while others wonder if we're seeing the fallout of a catastrophic cosmic event, like a collision between universes in the multiverse. But the biggest question of all might be what dark flow reveals about our place in the universe. If this current is real, our observable cosmos could be a mere eddy in a vast, unseen ocean. Are we floating toward some cosmic nexus, or is this motion a relic of imbalances from the Big Bang itself? The answers could redefine not just our understanding of space, but of time, existence, and the very nature of reality. And that's the true power of dark flow. It doesn't just challenge what we know, it forces us to confront how much we don't. Every telescope pointed at the void, every simulation run on supercomputers, brings us closer to truths that might be stranger than fiction. One day, we may look back at this enigma as the first clue in a story far grander than we ever imagined. Until then, the universe keeps its secrets flowing, silent and dark. From the eerie alignment of galaxy clusters moving in lockstep to the spine-tingling possibility of a neighboring universe tugging at ours, dark flow isn't just a mystery, it's a revolution in how we see the cosmos. Over the past 30 facts, we've peeled back layers of this enigma, revealing how it challenges everything from Einstein's gravity to the very idea that the universe expands evenly in all directions. We've watched galaxy clusters race toward the void at impossible speeds, traced the cold spot's ghostly imprint in the cosmic microwave background, and even dared to ask whether we're sensing the gravitational whisper of a reality beyond our own. Each discovery doesn't just add to the puzzle, it reshapes the board entirely. Think about what this means. For centuries, we've mapped the universe assuming it was isotropic, a featureless expanse where no direction was special. Dark flow shatters that illusion, hinting at hidden architectures, primordial imbalances, or even cosmic neighbors we'll never see. It's forced us to confront the unsettling truth that our observable universe might be a speck in something far grander, a current in a river whose source lies beyond the horizon. And the most thrilling part, we're only just beginning to ask the right questions, but dark flow's greatest lesson isn't in the answers it provides, it's in the questions it leaves hanging. Could the laws of physics change over cosmic distances? Is the multiverse more than a theoretical toy? Are we, right now, caught in a gravitational tide from a universe that vanished before ours began? These aren't just thought experiments, they're frontiers, waiting for the next generation of telescopes, simulations, and bold minds to explore. So as we close this cosmic journey, remember, the universe doesn't owe us clarity. It's under no obligation to make sense, and that's what makes dark flow so exhilarating. It's a reminder that the cosmos is stranger, wilder, and more mysterious than we ever imagined, and that every discovery, instead of settling the debate, only pulls us deeper into the unknown. The night sky isn't just a canvas of stars, it's a mirror reflecting back our endless curiosity. Keep looking up, keep questioning, because the next great cosmic revelation, it's out there waiting in the dark.